All right, students, welcome to your titration curve kind of summary walkthrough problems where we're going to consider all three titrations. You've learned about strong acid, strong base. You've learned about weak acid, strong base, and weak base, strong acid. And so this first question on page 3, question 8, is going to be more of a conceptual summary, and then we'll hop into an AP FRQ. So for this problem, I just want you to summarize what you know about these titrations. How can you identify them via graph? Okay. And what do we know it must be true about the equivalence point pH value? So for a net ionic equation, you can look up any example strong acid, strong base equation, and your net ionic would end up being some strong acid creating a hydronium ion plus some most likely oxide carrying base to produce two waters. And we do say it's liquid water, not aqueous water. If you were to look up a weak acid, strong base, okay, equation, you might look up, for me, I'm going to choose the example where I am titrating weak acid CH3COOH, a carboxylic acid, right, which is commonly weak. And what we say is, if that was the case, CH3COOH would be reacting with the OH of the strong base to produce, I have to jump down, sorry, water and the conjugate, carboxylate, with a -1 charge. And then if I were to look up another example of a weak base strong acid, I might choose NH3 ammonia, right? And some H plus proton, okay? And for a strong acid, and it would produce conjugate acid ammonium, polyatomic, and water. So that would be kind of what my net ionic equation would look like. Again, focusing on the actual ions and molecules involved in the reaction, ignoring spectators. So what would the titration curves of each one look like? Just a sketch if we assume that everything is pH on the vertical and everything is added titrant. So for the first one, I'm going to say that the added titrant is the strong base, such as NaOH. And what my curve would look like is I would start extremely low. And I know in the notes, I kind of exaggerated the curve of the beginning to compare it to the buffer region curve. But for the most part, it's actually relatively straight with a slight inflation, but it's like relatively straight. And then it goes up and it hits equivalence, and then it goes relatively flat with a slight bend to it, a slight inflation to the curve. And that would be an estimate. And we know that at equivalence, pH would be equal to 7. Okay. Now, when you compare this to a weak acid being titrated by a strong base, so again, I might say add NaOH for this. Okay. Here, what you have is one, your curve starts a little higher because it's a weak base. So it's not going to have such a strong hydrogen proton production. So that means that your pH is going to be higher because it's not producing as many hydrogen plus ions. So we're going to shift it up a little bit. And then what you'll notice is instead of the curve being relatively flat and slight bulbousness, now you get what we call a convex curve almost, where you get this region, the buffer region, and then it curves up, okay? And then it kind of mimics the same behavior where it goes flat at the end, pretty normal, okay? And I realized that was a little bit too curvy, but there we go. And here what we notice is our pH, okay, is going to be greater than 7. All right, because when we hit equivalence, we're going to have some conjugate base present, which is going to have its own hydrolysis or own acid-base reaction with the water producing OH minus. So what we see then is that our pH would be greater than 7. All right, and we have this interesting kind of buffer region. Okay, that for a weak acid, strong base is a little bit more convex, kind of curved up. And of course, we shifted it up a little bit. Now, what about the weak base strong acid? We too have a buffer region for this. And what we would say is our titrant would be adding strong acids such as HCl. Okay, I don't know, some type of strong acid. And what we have here is one, we start at actually a higher pH because we are titrating a base, but we wouldn't start at the highest pH, right? We wouldn't start at 14 because that would be a strong base. It'll start around like 11 or 10. And what happens is we actually get a concave nature to it, and then it goes down and curves. Okay. And so what we see is that our pH at equivalence is going to be less than 7. Why? Because now we have conjugate acid present in solution, which is going to have its own hydrolysis, its own acid-base reaction with the water when the weak base is completely neutralized, creating an overall more acidic solution at equivalence. And so that's kind of what we see here right now. And then what we have here is reason for equivalence point. I kind of explained all of that. So here pH is 7 because we are usually in a 1-to-1 ratio. If not 1-to-1, we see that the moles of base are completely neutralized by the moles of acid without any conjugates being present technically, because it creates a salt plus a water. For strong acid, strong base, you're creating a salt, an ionic compound that just dissociates. It doesn't really interact with the water in terms of creating a new compound. And water just adds more water molecules. So, and then for this one, we'd have the pH is going to be greater than 7 because what we have is conjugate, right? Base is producing OH minus with its own hydrolysis reaction. And by the way, a hydrolysis reaction is a neutralization between some type of charged species and water. Okay, with its own hydrolysis reaction with water. And then similar concept here, except we have a pH less than 7 because the conjugate acid, right, is copy. Oop. Erase this. The conjugate acid is producing its own H plus. Okay. Conjugate acid is producing its own H plus ion with the hydrolysis in water. Okay. So that's kind of your conceptual. Let's go ahead and hop down at question 7, AP question 7 in your workbook on page 17. And the relative data table that will be needed is going to be at the bottom of page 16. So what we're going to be asked here to do is we're going to be asked to kind of summarize our understanding of acid-base behavior with respect to buffer solutions. So a student prepares 3 solutions, X, Y, and Z, as given in the data table above. And we do have the values of Ka given below. So notice we have for 2 species, we have a super high Ka, which means we're super acidic. And if it's a Ka that can't even really be quantified because it's so large, we know it's a very strong acid. We also know that HBr structurally has a longer bond, and that Br minus is a very electronegative conjugate base, which means it'll be very stable. So we know that that is, of course, makes sense that we would have a super high Ka. And then, of course, we have this other weak acid with a very low Ka. All right, so we know that this is a weak acid. And so we're given this table down below, and we're given this table above regarding the specific solution information. Yeah, I guess that's the best way to put it. Use the information above, right, and write the letters of the solution in the boxes below to rank the solutions in order of increasing pH. So from most acidic to most basic. Explain your reasoning for the ranking. So for solution X, sorry, I'm making ice. For solution X, we have 100 milliliters of 0.1 molarity strong base, and it's mixed with 100 milliliters of 0.1 molarity strong acid. So we know that this is when we write out the equation, a strong base mixed with a strong acid, okay, which is going to be a standard one-to-one stoichiometric neutralization process. And when we look at the actual volumes that we used, we see that we do have the same volume. The moles equal of base stoichiometrically equal the moles of acid. So we know that we have achieved neutralization. So that means our pH is going to be equal to 7, okay? Now, how about Y? Okay, well, Y is a strong acid and its conjugate base, Br minus. Okay, we have the same data as far as volume and molarity goes. So we know that we're going to be equimolar. Okay. And what your mind might first say is, oh, strong, an acid plus its conjugate, buffer. But it's not a buffer because buffers can only occur with weak species. Okay, with weak species. And Br minus is not a strong base. It's actually, it's conjugate, to be honest. And so what we see is that we know that given the values of molarity and milliliters or volume used, we're going to have equal molar of the strong acid and its conjugate base. And remember, strong acids tend to produce weaker bases, okay? But since this is not a buffer, we're going to say that that strong acid is going to dominate the pH. So we know that we're going to have a low pH because of the strong acid present. As far as solution Z, we see a weak acid mixed with its conjugate base, where again, the Na is really just a spectator on it. It doesn't really do anything. And since this is a weak acid, okay, with its conjugate, we know that this is a buffer solution. So Z is a buffer solution. So we know that for Z, it's going to have a pH, all right, that given the value that the weak acid and conjugate base are equimolar, since we have the same amount of acid as we do conjugate base, we see that we are at halfway to equivalence for a buffer solution. And at halfway to equivalence, pH equals pKa. So if we did the pKa, the negative log of 1.8 times 10 to the negative fifth, which is the provided Ka value for this weak acid, we would find that the pH is equal to 4.74. Okay. And so then what we see is, as far as the order goes, we would say that X is the highest pH. It's the most basic out of all of them. It's neutral. Y is the lowest pH because that presence of strong acid, and because it is not a weak species, we would say that this is not a buffer solution, and Z is right in the middle due to the buffer behavior. Okay. So next question is, does the pH of solution Y increase, decrease, or remain the same when 100 milliliters of Y is added? So remember, Y is a strong acid plus its conjugate, but it's not a buffer solution. So if we add water, what we're doing is we are essentially, right, diluting the acid sample. Okay, and when we dilute the sample, what we see is that the concentration of H plus is going to decrease. Okay, and if the concentration of H plus decreases, what we see is that then the pH will increase. Okay, so pH will indeed increase. Okay, and you could put that in actual first sentences. So the pH will increase as the addition of water lowers the concentration of H plus, okay, in solution. C, the student adds 0.001 mole of NaOH to solution Y and adds 0.0010 moles of NaOH to solution Z. So right now we're adding strong base. Oops. We're adding strong base to both solutions. And it's equal molar, okay? Assume the volume of each solution doesn't change when the NaOH, so that we know that this is going to be a drop by drop. If the volume isn't changing, you're adding very small amounts of titrant, of base, okay? The pH of solution Y changes more than the pH of solution Z. Why? Well, okay, when we look at Y and Z, we've identified that Y is not a buffer solution, but Z is. So we know that according to, oh my goodness, what happened to our screen recording? Gee willikers, hold on. I think my thing logged me out. Give me a second to get me back on. Okay. So there we are. We're back on, guys. Sorry about that. Don't really know what happened, but let me get my screen content back on. Okay, there we go. So back to this question. We know that as we add things drop by drop, okay, in a non-buffer solution, such as solution Y is not a buffer, okay? In a non-buffer solution, such as solution Y, we'll see that the addition of NaOH will be far more effective in changing the pH than in solution Z, which is a buffer, and buffers stabilize pH when it's small amounts of titrant added. So solution Y is not a buffer, and therefore will be more affected by the addition of strong base, okay? But solution Z is a buffer solution, is a buffer solution. So it stabilizes, okay? Why can't I spell this? It stabilizes pH when small amounts are added. When small amounts of NaOH are added. Okay, so minus the scribbly scrabbly handwriting, there's kind of your short FRQ walkthrough. Remember, it is your responsibility to finish the workbook because this is your main practice for the AP 1 exam and 2 my test. And of course, there are more quizzes online and available where you really get to dig into this indicator, buffer, and weak acid, weak base titration. Okay, well, weak acid with strong base and weak base with strong acid titration curves and explanations of each region. So really good job, you guys, and best of luck.